In this video, we will look at how to use an energy bar chart to compare the amount of thermal energy in our system before and after a change. And then we will also do some simple problem solving with heat capacity, calculating the change in thermal energy in a system. First, energy bar charts. When it comes to energy, we can't draw particle diagrams to represent the change in energy in the system because energy is substance-like, but it is not a substance. It's not made of particles, it does not have mass, and it does not take up space. I use an analogy for money a lot of times when it comes to thinking about energy. And so in a bar chart, we're going to kind of keep track of how much energy is in our system with bar charts. Kind of like if you pull up your bank account online, you might see like a comparison of how much money you have in your account before and after you make a deposit or a withdrawal of energy. Of money. So here, in this energy bar chart, the first bar chart represents how much energy we have in our system before a change. The second bar chart represents how much of that energy we have in our system after the change. And the circle in the middle is where we identify what our system is going to be. So in this story, a cup of hot coffee cools as it sits on the counter. So the cup of coffee is our system. And you also can think about, well, what things are not in the system and draw them kind of outside the system. So like here, the kitchen counter is something that's outside of the system. Step 2 is we're going to add bars in our bar graph for the initial and final energy. It says the cup of hot coffee cools. So initially, we're going to have more thermal energy in the system. And after the cup of hot coffee cools, there will be less thermal energy inside the cup of coffee. So we're going to so we added bars for the initial and final energy account balances. Then we think about what happened in the system. And we're talking about thermal energy right now, which is energy associated with heat or temperature changes. So thermal energy is going to increase if the temperature increases. And it's going to decrease if the temperature decreases. So the third step is to determine how the amount of energy stored in the system changes from the beginning to the end. So we started with more energy in our system and ended with less energy in our system. The total amount of energy in the world cannot change. So we kind of have here in a picture or graph form, we have 3 somehow becoming 1. And so you think about, well, how did we go from 3 to 1? We subtracted 2. You don't have to draw this equation in your problem, but I'm kind of giving you how I'm thinking about it. So since energy is exiting our system, our cup of coffee has less energy now than it did initially. I'm drawing that arrow, and I made the arrow look like 2 little boxes to show that 2 units of energy left our system. We call this example an exothermic change, or an exothermic process, because energy exited our system. Now that we've done an example bar chart, we're going to look at some problem solving. How do we calculate the exact amount of energy in joules? Remember, we learned that joules are the unit for energy. We want to know whatever the mass is or whatever the temperature changes, how do we figure out how much energy is involved? Because we know that thermal energy depends on mass, it depends on temperature change, and it depends on what substance you have. We're going to start by focusing on water. So with a relationship always connects 2 or more units, it's always a ratio. Well, in our last set of notes, we define that relationship for thermal energy. It says that 4.18 joules of energy are needed to heat up 1 gram of water by 1 degree Celsius. It's different for other things, but we're going to stick with water for our first few examples. So following our same problem solving method that we've used all year, we're going to use this relationship and we're going to multiply or divide with the numbers in the problem. So it says how much energy is transferred if 1 gram of water is heated from 30 to 100 degrees Celsius. Well, we know it takes 4.18 joules for 1 gram to go up 1 degree Celsius. Well, in this case, the temperature change is 70 degrees Celsius because the temperature is going from 30 to 100. So we need 70 times as much energy. So we're going to take 70 degrees Celsius times 4.18 joules for 1 gram. And this is the amount of energy I got. So it takes 292.6 joules for 1 gram to go up 70 degrees Celsius. And I should also think about sig figs. 1.0 grams has 2 sig figs, and the 30 and the 100 each are accurate to the ones place. So when I subtract, the 70 is accurate to the ones place. So I've got 2 numbers, both with 2 sig figs. So this should be 290 joules for 1 gram to be heated up 70 degrees. Moving on to our second example. In this problem, we want to know how much energy is transferred if we're going to increase the temperature of some water by just 1 degree Celsius, but we want to increase the temperature of 100 grams of water. So again, we think about our relationship. It takes a little more than 4 joules for 1 gram to go up 1 degree Celsius. But we don't have just 1 gram, we have 100 grams. And so we need 100 times as much energy for 100 grams to go up 1 degree Celsius. So 100 times 4.18 is 418 joules for 1 degree Celsius. And since 100 grams has 3 sig figs, I'm going to leave the 418 joules for 1 degree Celsius. All right, so last example problem here, we're going to combine what we know. We know that thermal energy depends on mass. It depends on how much the temperature goes up or down, the change in temperature, and it depends on the substance. So we are going to again stick with water for now, but if we had a different substance, this relationship would work the same way, but it would just be a different value. So for water, there's 4.18 joules required for 1 gram to go up 1 degree Celsius. But in this problem, the temperature, well, instead of 1 gram, we've got 200 grams. So we need 200 times as much energy. But also, the temperature is changing, not just 1 degree, but the temperature is changing 65 minus 25, 40 degrees Celsius. And you do want to remember it's about temperature change. We focused on delta T when we discussed our lab. So since the temperature is changing 40 times as many degrees, we also need to multiply by 45 degrees Celsius. And notice, just like the first chapter, if we've got in our relationship grams on the bottom, we're going to multiply by grams because we don't want grams in our answer. We just want how much thermal energy in joules, the unit of energy, do we need to use. And notice we've also got a degree Celsius in the numerator and a degree Celsius in the denominator, which will simplify to 1. And so we're left with joules, and that is the units that we want for our answer for how much energy that we have. So we're going to take 200 times 40 times 4.18. I got 33,440 joules. If I go back and check sig figs, the way I have 200 written actually only has 1 sig fig. And the way I have my temperatures written, those each have 2 significant figures. So if I round this answer to just 1 significant figure, it would be 30,000 joules added. Oh, actually, sorry. In this case, we've got a back to that cup of hot coffee that we did our bar chart for a few minutes ago. Since the cup of coffee is cooling, that energy is going to be removed from our system. So 30,000 joules removed. I also have over here a temperature versus time graph. They're not going to be super helpful yet, but eventually later you will see that these are going to be the heart of our problem solving. So as time goes on, the coffee, we're just going to make a sketch of a graph. Doesn't need to be super careful, but we just want to think about the shape. The temperature starts at 65 and it's going to decrease to 25. So I'm going to assume the temperature will go down gradually, something like that. So now it is your turn to do some problem solving, and the heat capacity for water or whatever substance that you're going to be using, the heat capacity is going to be the basis for all of your problem solving, and it's going to be one of our big relationships in this chapter.